All right, so we're going to talk about all the different acid chloride derivatives now in the order of most reactive to least reactive. And essentially, the situation is if you're starting with something that's more reactive, it's very easy to go from the higher reactivity to the lower activity states. So, what's the most reactive carboxylic acid derivative? Acid chlorides. These are the most reactive, so they can be used to access any derivative. So we're going to talk now a little bit about the mechanism of how these work and why they work the way they do. And essentially, again, we should be trying to reason out the steps of this mechanism instead of just memorizing, oh, acid chlorides are the most reactive, they just make anything else. So first step in this reaction mechanism, we have a big partial positive right there. So something that is partially negative is going to flow to that. So what is partially negative over here? The most electronegative atom of either pyridine or our water molecule is the oxygen. So step one, the partially negative oxygen is attracted to the partially positive carbonyl carbon. So this would be step one of this reaction. That would produce our tetrahedral intermediate, where we have the ability for these electrons to come down and essentially kick out either of those leaving groups. And in this form, the chlorine is probably the best leaving group. But this OH2 plus is also still really unstable being bonded here. It's even more unstable than hydronium ion by itself because it has these electronegative atoms pulling electron density away from itself. So it's making it even more partially positive. So that's why we have the pyridine in solution. Essentially, the pyridine is that moderate base that essentially is going to pick up any protons that are relatively acidic. This is a strongly acidic proton, so we have our weak or moderate base pyridine, and this is going to be a favorable equilibrium. Why is that? Well, even if we just assume that this is a similar acidity to hydronium ion, we know that the H3O plus pKa is negative 1.7. So why would this reaction happen? Well, what are we forming? We're forming our tetrahedral intermediate that is still ready to collapse down and kick out the best leaving group, and our pyridinium ion. This isn't exactly the same thing as NH4+, but it's close enough to where the pKa of this is still relevant to this discussion, and the pKa of ammonium is 9. So why did step 2 happen? Step 2 happened because we know acid-base reactions are going to happen if they're favorable, and we flowed away from the stronger acid. So that provides this tetrahedral intermediate where one of the leaving groups, the chlorine, is much more stable on its own than OH minus. So essentially, these electrons are going to come down, kick out the best leaving group to provide our carboxylic acid from that acid chloride. And we can also write that we have Cl minus in there. So again, a very much downhill reaction because we're forming a more stable carboxylic acid derivative from a more reactive carboxylic acid derivative. What else can we make with acid chlorides? And acid chlorides are the most reactive carboxylic acid derivative. So we can literally make any other carboxylic acid derivative from them. This carboxylate could be used, so this would just be potassium acetate. That O minus is going to be attracted to the carbonyl carbon. It would add in there. We'd form our tetrahedral intermediate. There's no acid-base chemistry that has to occur this time because this is already in the anion state. So then that tetrahedral intermediate would collapse back down to reform the carbonyl, and it would kick out chlorine. So that would form the anhydride. So this is the bond that was just formed by that O- adding to that carbonyl. What about if we treat it with an alcohol? Well, an alcohol is pretty much the exact same reactivity as a water molecule. We need the pyridine again to pull off that proton that is acidic. And it's going to go through the exact same mechanism that we just discussed with water to form our ester. So whatever that R is would be the R group that the ester would now have. What about amines? If we have an amine, again, our amine, the nitrogen is partially negative. That's going to be attracted to the carbonyl carbon. And why do we say greater than 2 equivalents of ammonia here? Greater than 2 equivalents of our primary or secondary amine? Well, this first step is going to generate that tetrahedral intermediate. And what might another equivalent of an amine do at this point? Well, we saw pyridine act as a base to deprotonate the intermediate, and that same thing is likely to happen here. These hydrogens are relatively acidic, and NH3 is a moderate base, so if one equivalent of an amine adds in, another equivalent of an amine is going to act as a base to deprotonate that intermediate. So that would provide us with the tetrahedral intermediate that would then collapse down and kick out that chlorine ion to provide us with the amide product. So that would be the amide. We have Cl-, and we also have NH4+. So again, acid chlorides, really reactive carboxylic acid derivative. We can make anything from them, any carboxylic acid derivative at least.